In this tutorial, we will see how to perform exponential smoothing with both trend and seasonal adjustments as calculated in the 10th edition of the Service Management Textbook by Bordoloi. Two notes are in order. First, the textbook calculates these problems using a tabular approach, only the table is not completed from left to right. Instead, the calculations jump around. We will follow the approach in the textbook. Second, there are several errors in the calculations as presented in the textbook. These errors are minor, and we will follow the approach in the textbook since you are no doubt watching this tutorial in order to understand the textbook's calculations. The screen shows 2 years of actual demand. We will be using the first year to produce the forecast. Once we have a forecast, we will use the second year to compute a MAD for the forecast. Note that the alpha value we will be using for this forecast is 0.3, the beta value is 0.1, and the gamma value is 0.3. The first step is to average the actual demand for the first year, 2,215 plus 1,654 plus 2,330 plus 2,519 plus 3,044 plus 3,536 plus 4,119 plus 4,473 plus 3,657 plus 3,186 plus 2,340 plus 2,903, all divided by 12, equals 2,998.00. This value is not shown on the screen, but will be used in the next set of calculations. We are now ready to calculate the indices for each of the 12 months. These indices are calculated as the ratio of the month's actual demand to the average demand of 2,998 we just calculated. For January, 2,215 divided by 2,998 equals 0.740. Note that we will be rounding these values to 3 decimal points. For February, 1,654 divided by 2,998 equals 0.552. For March, 2,330 divided by 2,998 equals 0.777. For April, 2,519 divided by 2,998 equals 0.840. For May, 3,044 divided by 2,998 equals 1.015. These 12 indices will always sum to 12, with perhaps small rounding errors, so some of them must be larger than 1. For June, 3,536 divided by 2,998 equals 1.179. For July, 1,119 divided by 2,998 equals 1.374. For August, 4,473 divided by 2,998 equals 1.492. For September, 3,657 divided by 2,998 equals 1.220. For October, 3,186 divided by 2,998 equals 1.063. For November, 2,340 divided by 2,998 equals 0.781. For December, 2,903 divided by 2,998 equals 0.968. These indices we just computed will be used to deseasonalize an exponentially smooth forecast for the first year. However, we must first seed the forecast. To do that, we set F12 equal to A12, or 2,903 in this case. Once we begin calculating these, we will maintain 2 decimal points. We also need to seed the trend component, that is, the T12 value. Unless the problem tells you otherwise, you always seed the trend with a starting value of 0, as we have done here. You cannot compute all of the values for S sub t and then all of the values for T sub t. That is, you cannot go column by column. Instead, you must go row by row, as we will do here. That is, S13, T13, S14, T14, S15, T15, and so on. The formulas to calculate S sub t and T sub t are shown on the screen. Note that since we are seeding in December, these formulas are not yet being used. For January, S sub t equals 0.2 times 2,921 divided by 0.740 plus 1 minus 0.2 times 2,903 plus 0 equals 3,111.86. And for T sub t, 0.1 times 3,111.86 minus 2,903.00 plus 1 minus 0.1 times 0 equals 20.89. For February, S sub t equals 0.2 times 2,804 divided by 0.552 plus 1 minus 0.2 times 3,111.86 plus 20.89 equals 3,522.14. And for T sub t, 0.1 times 3,522.14 minus 3,111.86 plus 1 minus 0.1 times 20.89 equals 59.83. For March, S sub t equals 0.2 times 2.846 divided by 0.777 plus 1 minus 0.2 times 3,522.14 plus 59.83 equals 3,598.13. And for T sub t, 0.1 times 3,598.13 minus 3,522.14 plus 1 minus 0.1 times 59.83 equals 61.44. For April, S sub t equals 0.2 times 3,169 divided by 0.840 plus 1 minus 0.2 times 3,598.13 plus 61.44 equals 3,682.18. And for T sub t, 0.1 times 3,682.18 minus 3,598.13 plus 1 minus 0.1 times 61.44 equals 63.70. For May, S sub t equals 0.2 times 3,473 divided by 1.015 plus 1 minus 0.2 times 3,682.18 plus 63.70 equals 3,681.04. And for T sub t, 0.1 times 3,681.04 minus 3,682.18 plus 1 minus 0.1 times 63.70 equals 57.22. For June, S sub t equals 0.2 times 4,391 divided by 1.179 plus 1 minus 0.2 times 3,681.04 plus 57.22 equals 3,735.48. And for T sub t, 0.1 times 3,735.48 minus 3,681.04 plus 1 minus 0.1 times 57.22 equals 56.94. For July, S sub t equals 0.2 times 4,596 divided by 1.374 plus 1 minus 0.2 times 3,735.48 plus 56.94 equals 3,702.93. And for T sub t, 0.1 times 3,702.93 minus 3,735.48 plus 1 minus 0.1 times 56.94 equals plus 47.99. For August, S sub t equals 0.2 times 4,917 divided by 1.492 plus 1 minus 0.2 times 3,702.93 plus 47.99 equals 3,659.85. And for T sub t, 0.1 times 3,659.85 minus 3,702.93 equals 1 minus 0.1 times 47.99 equals 38.88. For September, S sub t equals 0.2 times 4,109 divided by 1.220 plus 1 minus 0.2 times 3,659.85 plus 38.88 equals 3,632.60. And for T sub t, 0.1 times 3,632.60 minus 3,659.85 plus 1 minus 0.1 times 38.88 equals 32.27. For October, S sub t equals 0.2 times 3,858 divided by 1.063 plus 1 minus 0.2 times 3,632.6 plus 32.27 equals 3,657.76. And for T sub t, 0.1 times 3,657.76 minus 3,632.60 plus 1 minus 0.1 times 32.27 equals 31.56. For November, S sub t equals 0.2 times 3,275 divided by 0.781 plus 1 minus 0.2 times 3,657.76 plus 31.56 equals 3,790.13. And for T sub t, 0.1 times 3,790.13 minus 3,657.76 plus 1 minus 0.1 times 31.56 equals 41.64. For December, S sub t equals 0.2 times 3,373 divided by 0.968 plus 1 minus 0.2 times 3,790.13 plus 41.64 equals 3,762.32. And for T sub t, 0.1 times 3,762.32 minus 3,790.13 plus 1 minus 0.1 times 41.64 equals 34.70. This completes the calculation of the smooth values. Unlike simple exponential smoothing, we will not be going one period into the future. The next step is to revise the indices based on the additional year's worth of actual values. These revised values are not used in any of the calculations for this problem. That is, they are informational only. They will be used to forecast for year 3 were that required. Rather than being calculated as a ratio of actual demand to average demand, as we did for the first set of indices, those first set of indices are updated using a process similar to simple exponential smoothing. The formula is the index for time period t equals gamma times the ratio of the actual for time period t divided by the smooth value for time period t plus 1 minus gamma times the index for 1 year ago, that is period t minus L. Recall that gamma equals 0.3 and that will not change. The index for January, I sub 13 equals 0.3 times 2,921 divided by 3,111.86 plus 1 minus 0.3 times 0.740 equals 0.800. The index for February, I sub 14 equals 0.3 times 2,804 divided by 3,522.14 plus 1 minus 0.3 times 0.552 equals 0.625. The index for March, I sub 15 equals 0.3 times 2,846 divided by 3,598.13 plus 1 minus 0.3 times 0.777 equals 0.781. The index for April, I sub 16 equals 0.3 times 3,169 divided by 3,682.18 plus 1 minus 0.3 times 0.840 equals 0.846. The index for May, I sub 17 equals 0.3 times 3,473 divided by 3,681.04 plus 1 minus 0.3 times 1.015 equals 0.994. The index for June, I sub 18 equals 0.3 times 4,391 divided by 3,735.48 plus 1 minus 0.3 times 1.179 equals 1.178. The index for July, I sub 19 equals 0.3 times 4,596 divided by 3,702.93 plus 1 minus 0.3 times 1.374 equals 1.334. The index for August, I sub 20 equals 0.3 times 4,917 divided by 3,659.85 plus 1 minus 0.3 times 1.492 equals 1.447. The index for September, I sub 21, equals 0.3 times 4,109 divided by 3,632.6 plus 1 minus 0.3 times 1.220 equals 1.193. The index for October, I sub 22 equals 0.3 times 3,858 divided by 3,657.76 plus 1 minus 3.3 times 1.063 equals 1.061. The index for November, I sub 23, equals 0.3 times 3,275 divided by 3,790.13 plus 1 minus 0.3 times 0.781 equals 0.806. The index for December, I sub 24, equals 0.3 times 3,373 divided by 3,762.32 plus 1 minus 0.3 times 0.968 equals 0.947. That's a lot of work for values we will not be using for the rest of the problem. Anyway, these indices were computed using a different method, so there is no requirement that they sum to 12, although they will be close. In this case, they sum to 12.012. The forecast formula is the forecast for time period t plus 1 equals S sub t plus t sub t, all times I sub t minus L plus 1. That is, the seasonal index for the same period last year. Stated another way, the forecast for the next period equals the smooth value for this period plus the trend value for this period, all times the seasonal index for the same period last year. The formula just given is the one we will be using, but the T+1 notation can be confusing. Just to clarify, the equation yields the same value as the forecast this period equals the smooth value for the last period plus the trend value for the last period, all times the seasonal index for the same period last year. We have the values for period 12 and could compute a forecast for January, but the textbook skips this period, so we will skip it as well. This is one of two errors in the textbook's approach. I will discuss the second error in a moment. The forecast for February equals 3,111.86 plus 20.886 times 0.552 equals 1,729. We will always round the forecast to a whole number. Here, you see the second error in the textbook's approach. The forecast for February should be calculated as the smooth value for February plus the trend for February times the February index. Instead, the textbook uses the January smooth and trend values. This error is repeated for each month. So basically, the smooth values always lag one period behind what it should be. This is incorrect, but is what the textbook does, and is how the answer key is computed for the instructor's manual, so we will use this incorrect approach. Unlike when the textbook made the same error when calculating an exponentially smooth forecast with seasonal data, this data has a trend component. Here, with a trend, it has a larger impact. As we will see later, this forecast has a MAD of 368. Were it calculated correctly, its MAD would drop to 336. Additionally, when we look at a chart of the actual versus forecast, notice how far off the forecast for period 13 is. The forecast catches up quickly, but it does show the error. Nevertheless, you came to this tutorial to understand the textbook approach, so that is the approach we will be using, errors and all. The forecast for March equals 3,522.14 plus 59.825 times 0.777 equals 2,783. And remember, we are rounding to whole numbers. The forecast for April equals 3,598.13 plus 61.442 times 0.840 equals 3,074. The forecast for May equals 3,682.18 plus 63.703 times 1.015 equals 3,802. The forecast for June equals 3,681.04 plus 57.219 times 1.179 equals 4,407. The forecast for July equals 3,735.48 plus 56.94 times 1.374 equals 5,211. The forecast for August equals 3,702.93 plus 47.992 times 1.492 equals 5,596. The forecast for September equals 3,659.85 plus 38.885 times 1.220 equals 4,512. The forecast for October equals 3,632.6 plus 32.271 times 1.063 equals 3,896. The forecast for November equals 3,657.76 plus 31.56 times 0.781 equals 2,881. The forecast for December equals 3,790.13 plus 41.641 times 0.968 equals 3,709. I have all of the forecast values. These values include seasonality and trend. We will wrap it up by computing the forecast error and then the MAD. For the absolute value of the error terms, 2,804 minus 1,729 equals 1,075. 2,846 minus 2,783 equals 63. 3,169 minus 3,074 equals 95. 3,473 minus 3,802 equals 329. And remember, we are ignoring negative signs. 4,391 minus 4,407 equals 16. 4,596 minus 5,211 equals 615. 4,117 minus 5,596 equals 679. 4,109 minus 4,512 equals 403. 3,858 minus 3,896 equals 38. 3,275 minus 2,881 equals 394. 3,373 minus 3,709 equals 336. While not shown on the screen, these values average to a MAD of 368. The screen now shows a graph of the actual versus the forecast. As you can see, except for the first period, the forecast tracks actual very closely. It tracks both the seasonality and the trend very well. It's not part of the textbook, but let's discuss how we can extend the forecast for another year. This technique is designed for demand with a seasonal component and a trend component. If there was no seasonality, we would use trend-adjusted exponential smoothing technique. If it had seasonality but not trend, we would use the exponential smoothing with seasonal adjustment approach. We are forecasting, so there are no actual values at this point. That means we will be unable to revise the MAD once we have the forecast. Without actuals, we cannot update the S sub t smooth values going into the future. Our best estimate of these values is S sub 24, so that will be our S value for all 12 months. You might be wondering why we're not using the old January value for this January, the old February value for this February, and so on. The reason is simple. The old January value is missing part of the trend from February, February is missing part of the trend from March, and so on. Some of that trend is picked up by the t value, but you can see that the S sub t grows from 3,111 in January to 3,762 in December, so some of it remains in the smooth values. Without new actual data, we cannot revise the trend component, so we're using the values from last year. Without new actual data, we cannot update the seasonal indices. That's fine. Recall that the update we calculated as part of the problems were not used. They were not used because they were intended for year 3. That is what we are now computing, so we will use those second set of indices. We have not copied them down to this table because once we get the actual values, we will be updating the indices here for year 4. The forecasts for all 3 years are shown on the screen. We will not be showing the calculations individually or narrating all of them, as we've already seen how to perform these calculations. Nevertheless, the first few calculations are as follows. F sub 25 equals 3,762.32 plus 34.70 quantity times 0.800 equals 3,036. F sub 26 equals 3,762.32 plus 20.89 quantity times 0.625 equals 2,365. F sub 27 equals 3,762.32 plus 59.83 quantity times 0.781 equals 2,986. F sub 18 equals 3,762.32 plus 61.44 quantity times 0.846 equals 3,236. The rest are calculated the same way. Since we do not have actual demand, we cannot compute the error terms or the MAD. The screen now shows a graph of the extended forecast. Notice how well the extra year tracks both the seasonality and trend of the first 2 years. The screen now shows a second example for you to try. Use an alpha value of 0.3, a beta value of 0.2, and a gamma value of 0.4.
Since you've seen an example already, let me suggest that you pause the video and try to work this problem on your own. Once you're done, you can use the video to check your work and spot any mistakes you might have made.
Please note that due to the number of calculations and their repetitive nature, I will not be narrating the calculations in as much detail as I did in the first example. The average of the first 12 actual values is 3,531.00. 2,754 divided by 3,531 equals 0.780. 2,169 divided by 3,531 equals 0.614. 2,843 divided by 3,531 equals 0.805. The rest of the values are computed the same way. Pause the video and check your work so far. If you made a mistake, please rework the problem before continuing. We next seed the smooth and trend values. We let S sub 12 equals A sub 12 equals 3,422 and let T sub 12 equals 0. We are now ready to compute the S and T values going forward. The formulas we will be using are shown on the screen. Remember, you cannot go column by column. That is, you cannot calculate all of the S sub T values first and then calculate all the values of T sub T. Instead, you must go row by row. that is S13, T13, S14, T14, S15, T15, and so on. S sub 13 equals 0.3 times 3,460 divided by 0.780 plus 1 minus 0.3 times the quantity 3,422 plus 0 equals 3,726.17. T13 equals 0.2 times 3,726.17 minus 3,422 plus 1 minus 0.2 times 0 equals 60.83. S14 equals 0.3 times 3,337 divided by 0.614 plus 1 minus 0.3 times the quantity 3,726.17 plus 60.83 equals 4,281.36. T14 equals 0.2 times 4,281.36 minus 3,726.17 plus 1 minus 0.2 times 60.83 equals 159.70. S15 equals 0.3 times 3,384 divided by 0.805 plus 1 minus 0.3 times the quantity 4,281.36 plus 159.7 equals 4,369.86. T15 equals 0.2 times 4,369.86 minus 4,281.36 plus 1 minus 0.2 times 159.7 equals 145.46. S sub 16 equals 0.3 times 3,697 divided by 0.859 plus 1 minus 0.3 times the quantity 4,369.86 plus 145.46 equals 4,451.88. T16 equals 0.2 times 4,451.88 minus 4,269.86 plus 1 minus 0.2 times 145.46 equals 132.78. The rest of the values are computed the same way. Pause the video and check your work so far. If you made a mistake, please rework the problem before continuing. We are now ready to update the indices. The formula to do that is shown on the screen. Remember, these are informational only and are not used for the remainder of the problem. I13 equals 0.4 times 3460 divided by 3,726.17 plus 1 minus 0.4 times 0.780 equals 0.839. I14 equals 0.4 times 3,337 divided by 4,281.36 plus 1 minus 0.4 times 0.614 equals 0.680. I15 equals 0.4 times 3,384 divided by 4,369.86 plus 1 minus 0.4 times 0.805 equals 0.793. I16 equals 0.4 times 3,697 divided by 4,451.88 plus 1 minus 0.4 times 0.859 equals 0.848. The rest of the values are computed the same way. Pause the video and check your work so far. If you made a mistake, please rework the problem before continuing. We are now ready to calculate the forecast. The formula to do that is shown on the screen. And remember, we are rounding the forecast to a whole number. F14 equals 3,726.17 plus 60.83, all times 0.614 equals 2,325. F15 equals 4,281.36 plus 159.70, all times 0.805 equals 3,575. F16 equals 4,369.86 plus 145.46, all times 0.859 equals 3,879. F17 equals 4,451.88 plus 132.78, all times 1.01 equals 4,631. The rest of the values are computed the same way. Pause the video and check your work so far. If you made a mistake, please rework the problem before continuing. We're finally ready to calculate the absolute value of the error terms. 2,325 minus 3,337 equals 1,012. And remember, we're ignoring the negative signs. 3,575 minus 3,384 equals 191. 3,879 minus 3,697 equals 182. 4,631 minus 3,984 equals 647. The rest of the values are computed the same way. Pause the video and check your work so far. If you made a mistake, please rework the problem before continuing. Our final step is to average the absolute error terms. That yields a MAD of 471. If you got that correct, you likely got everything correct. Finally, the screen shows a graph of the actual demand versus the forecast. Just like last time, the fit is fairly good except for the first period of the forecast. Extending this for another year is left to interested listeners. If this video helped you working operations management problems, please consider liking the video and subscribing to the channel.